Hello and welcome to the second video of real analysis. In this video we're going to study real series and their convergence. Along the way we'll introduce a very important test for convergence called the ratio test, and this, along with manipulation of geometric series, will be useful tools later in the course. Crucially, we will see that the tools developed for real series and convergence can also be extended to complex series. As a quick recap of what we looked at in the previous video, we looked at the limits of a real function, we looked at differentiation of a function as a limit, and we ended by looking at integration and defining it as the continuum limit of a sum. Here are the intended learning outcomes for this video. After watching this video, you should be able to define absolute convergence of a series. You should be able to use the ratio test to test a series for convergence. And you should also be able to manipulate geometric series in order to find series expressions for functions. We're going to be talking about series and convergence. Now, a series is nothing more than a sum of terms. When we're dealing with, e.g., power series, which come up a lot in physics, we're often interested in summing an infinite number of terms. So we're often interested in infinite series. We write these as the sum from n equals 0 to infinity of terms a subscript n. And this is a0 plus a1 plus a2, and so on. Now, what does it mean for a series to converge? Well, we can only assign a finite value to such an infinite series, to such a sum, if it converges. So how do we check for convergence? Well, one way is to begin by defining partial sums. So we define partial sums. So partial sums as S subscript n, and this is the sum of the terms from n equals 0 to capital N of an. So there are a total of n plus 1 terms in this partial sum. Now the infinite series converges if the sequence of partial sums, so a sequence is just a list of numbers, so if the sequence of partial sums tends to a finite value, S, as the number n tends to infinity. We can write this as the limit, as n tends to infinity, of the partial sums is this finite value S. And we can write this as, and I'll write out what this means in words afterwards in case the notation is a bit obscure. So this means that for every epsilon greater than 0, there exists some n0 such that the distance between the value to which the series converges, S, and the partial sum Sn is less than epsilon for all n greater than n0. Okay, so let's unpack this. So I'm going to write out what this means in words. So this means, i.e., we can always find some index n0 above which every index n gives a corresponding partial sum Sn that is within epsilon of S. What this means is if you give me some small positive number epsilon, then I can always find a partial sum Sn that is within epsilon of the value of convergence. So if this statement above holds, then the infinite series converges, and we define the value it converges to. S is the sum from n equals 0 to infinity of these terms. Now, checking this limit of partial sums is not always practical, but one way of testing convergence is Cauchy's criterion. Cauchy's criterion. Let's define the sequence of partial sums for some infinite series as, so a sequence is just a list of numbers, and in this case the numbers are the partial sums. So we'll have S0, S1, S2, up to Sn, and so on. Now the first term in the sequence is going to be A0, the next is going to be A0 plus A1, then A0 plus A1 plus A2, and then the partial sum Sn is the sum from n equals 0 to n of An, and so on. Cauchy's criterion says that the infinite series converges if and only if, so that's if with two f's, if and only if the following statement holds. So as before, I'm going to write down the statement using mathematical notation first, and then I'm going to unpack it in case that's a bit obscure. So Cauchy's criterion says that the infinite series converges if and only if for all epsilon greater than 0, there exists some n0 such that the distance between the mth partial sum and the nth partial sum is less than epsilon for all m greater than n greater than n0. Okay, so what does this mean? This means, i.e., given some small positive epsilon, you can always find a point n0 in the sequence of partial sums beyond which all elements, so all partial sums, are within epsilon of each other. To make this a bit clearer, we can think about what's going on the real number line, where we're going to place our partial sums. So let's suppose that the value of convergence is given on the right-hand side by S. Then we can put the partial sum with index n0 minus 1 over here, and then maybe S n0 goes over here. And then beyond this point, all partial sums are within epsilon of each other. So Sn0 plus 1 might be here. This is epsilon. And then this would be Sn0 plus 2, and so on. So to quickly reiterate, what this means is, if you give me some small positive epsilon, no matter how small epsilon is, I can always find partial sums that are at least that close, which have indices greater than some given value n0. We'll look at a more practical test for convergence in a moment, but first of all we're going to briefly discuss absolute and conditional convergence. What is meant by absolute convergence? If the infinite series of the absolute values of terms, so here I'm omitting the index running from n equals 0 to infinity, but it's implicit. So here I'm summing the absolute value of the terms an. So if this infinite series converges, then the sum of the infinite series of terms where I don't take the absolute value also converges. So such an infinite series here is termed absolutely convergent. It turns out that if a series is absolutely convergent, this means that terms within this absolutely convergent series may be reordered without affecting convergence of the series. And we can prove this quite easily, and we'll be making use of the triangle inequality that we encountered for complex numbers in topic 1. So to prove this, if the infinite series of the absolute value of terms converges to some value, then Cauchy's criterion holds. This is the criterion that we encountered a few minutes ago. Now, Cauchy's criterion holds. That means, therefore, for any positive epsilon, the distance between the mth and the nth partial sums is less than epsilon for m greater than n greater than n0. Now, if we substitute in the expressions for the partial sums, so that's the sum of a finite number of the absolute value of terms, it turns out that this quantity here we can write down as the absolute value of an plus 1, the absolute value of an plus 2, all the way up to am minus 1 and am. And this sum of absolute terms is less than epsilon. We're now going to use the triangle inequality. So by the triangle inequality, the absolute value of the sum is less than or equal to the sum of the absolute values. So we can write this as the absolute value of an plus 1 plus an plus 2 all the way up to am minus 1 plus am. This is less than or equal to the sum of the absolute values. up to a m minus 1 and a m. And from the line above, we know that this is less than epsilon. It's worth quickly pointing out how this relates to the triangle inequality we met in topic 1. In topic 1, we were looking at the magnitude of the sum of complex numbers, and we related this to the length of vectors in the complex plane. If we're dealing with real series, then these terms an can be positive or negative. And because the set of real numbers is contained in the set of complex numbers, the triangle inequality still applies here. What we have on the left-hand side is the absolute value of the difference of partial sums Sm primed and Sm primed, where S primed n are partial sums of the series of the terms an. Hence, again by Cauchy's criterion, the sequence of partial sums infinity and sum n equals 0 an also converges. Therefore, this infinite series converges. So we've now established what absolute convergence means. What about conditional convergence? So on the other hand, if the sum of the absolute value of terms diverges, but the sum of the terms alone converges, then we say that this series here is conditionally convergent. This means that rearranging the order of terms can affect behavior of the sum. And as a quick example of this, there's something called the alternating harmonic series. Alternating harmonic series. And this has terms 1 minus a half, plus 1/3, minus a quarter, plus a fifth, and so on. Turns out that this converges to ln 2. If instead we shuffle terms around and we try 1 plus 1/3 minus a half plus a fifth plus 1/7 minus a quarter and so on, this converges to 3/2 of ln 2. So for conditionally convergent series, the order of the terms matters. A quick final point. Note that a necessary condition for convergence is that the terms get small as n approaches infinity. So as n approaches infinity, the terms approach 0. But this condition alone is not sufficient for convergence. And as an example, the harmonic series, which is given by the sum from n equals 1 to infinity of 1 over n, in other words 1 plus a half plus a third, etc. So even though these terms do indeed approach 0 as n approaches infinity, the harmonic series diverges. We're now going to quickly cover a very important test of convergence that you can apply to the series directly. This is called the ratio test. In the ratio test, we take the limit as n approaches infinity of the ratio of the n plus 1th to the nth term in the series. Now, if this limit exists, then we have three possibilities. If the limit is less than 1, then the series converges absolutely. If the limit is greater than 1, then the series diverges. And if the limit equals 1, then the test is inconclusive. And you need another test. And an example of this is what we saw above in the harmonic series. It's easy to check that as n tends to infinity, this quantity becomes n divided by n plus 1. And as n tends to infinity, that approaches 1. So these are the three values of interest for the ratio test. I'm not going to go through the proof now, but you can look it up in Riley, Hobson and Bentz or Arfken, which are both in the resource list on Blackboard. I'll quickly note that this is convenient because it can be applied to the series directly. And you'll get some practice of this in the problem sheet. We're now going to talk about a very important example of an infinite series called the geometric series. The geometric series are defined like this. The sum from n equals 0 to infinity of t to the n. Its partial sums are Sn, the sum from n equals 0 to n of t to the n. So this is given by t to the 0 plus t to the 1 plus t squared all the way up to t to the n. Note that t times this partial sum gives you t to the 1 plus t squared all the way up to t to the n plus 1. So if we take t times the partial sum Sn and subtract Sn, then all of the common terms here and here cancel, and we're left with t to the n plus 1 minus t to the 0. And you can rearrange this to give you that the partial sum Sn is t to the n plus 1 minus 1, which is t to the 0, divided by t minus 1. And this assumes that t does not equal 1, because then the denominator equals 0. Let's now consider testing the geometric series for convergence. We could apply the Cauchy criterion to the partial sums, but in fact for most of the rest of this course we're going to be using the ratio test a lot. So to get practice with it, let's use the ratio test here. So, applying the ratio test, we have that the limit, as n tends to infinity, of the n plus 1th over the nth term absolute value. Here this is given by t to the n plus 1 over t to the n, absolute value. This is just the absolute value of t. Now the ratio test says that a series converges if this limit is less than 1. Therefore, the geometric series converges if the absolute value of t is less than 1. In this case, it's also easy to check that when t equals 1, the geometric series then gives us the sum of t to the n, which here will just be the sum of 1. And this obviously diverges. On the other hand, if t equals minus 1, then the series gives us the sum from n equals 0 to infinity of minus 1 to the n. In other words, 1 minus 1 plus 1 minus 1, and so on. It's easy to see that the partial sums oscillate between 0 when n is even and 1 when n is odd. Therefore, the geometric series when t equals minus 1 does not converge. Observe that the ratio test told us that the absolute value of t was less than 1, which means that minus 1, so t lies between minus 1 and 1. This is an interval of convergence. And it's important to note that usually you have to check explicitly what happens at the boundary of this interval separately to find out whether or not the series converges there. This interval of convergence will be generalized later to a radius of convergence. So radius of convergence in the complex plane for complex numbers. The very last thing to discuss in this video is to what value does the geometric series converge when t lies between minus 1 and 1. So to what value does the series converge when t lies between minus 1 and 1? Well, here we can take the limit of partial sums. We can consider the limit as n tends to infinity of the partial sum Sn. And we wrote down the value of this earlier. It's the limit as n tends to infinity of t to the n plus 1 minus 1 over t minus 1. Now, because the absolute value of t is less than 1, as n tends to infinity, this t to the n plus 1 is going to approach 0. This gives us 0 minus 1 over t minus 1, and this is just 1 over 1 minus t. This is an extremely important result. So we have that the sum of a geometric series, which is given by 1 plus t squared, and so on to infinity, is given by 1 over 1 minus t, where t lies between minus 1 and 1. And this is so important, I'm going to put a red box around it. I'll note that this is an important tool we'll use throughout the course. That's the end of this second video of Topic 2, Real Analysis. To quickly recap, we've used the limit of partial sums to define convergence of a series. We've made the distinction between absolute and conditional convergence of series, and we found that for absolutely convergent series, the ordering of terms does not affect the convergence. We also covered the ratio test for convergence that you can apply to the series directly, and it's very useful and you'll get lots of practice of it in the problem sheet. Finally, we ended with a discussion about geometric series, and we identified conditions for when a geometric series converges and to what value it ends up converging to. So thanks for listening, and up next is video 3.